Hi everyone, I am Dongdong, a PhD student from Columbia University. Today I'm going to present MTFuzz, a machine learning-based fuzzer with multitask neural network. Here is a workflow of a typical coverage-guided fuzzer. It starts with the seed coppers, then generate tests through random mutation, execute on target program, measure edge coverage. If there are new edge found, the test input will be saved, else the test input is discarded. A typical example is AFL. It is effective, scalable, and easy to use, but they often get stuck after a while of running and generate a lot of uninteresting inputs, which fails to explore new edges because the underlying random mutation scheme fails to learn from past experience and the hot bias distribution of input are ignored. To address these problems, a popular approach is to use machine learning-based fuzzing. Machine learning-based fuzzing would use a neural network to approximate certain program property, such as branching behavior, then use the neural network to guide fuzzer to generate effective mutations or filter unpromising mutations. This graph shows an example of machine learning-based fuzzing. Given an input fitted on real-world program, we can obtain its corresponding edge coverage. Machine learning-based fuzzing uses a neural network to learn a surrogate of program behaviors by predicting the edges for given inputs. Further, the trained neural network can guide the fuzzer to generate effective mutations. Although it's effective in practice, it has three major limitations. First, the input space, representing the input byte sequence, is highly dimensional and sparse. Second, the training sample of neural net model are collected from interesting inputs generated by fuzzers. Since fuzzers normally maintain a limited number of interesting inputs for performance consideration, the neural network often lacks of enough training samples. Third, the edge coverage is coarse-grained. It only records the edges exercises during dynamic execution, while fail to capture other information, such as state of calling stack, distance of unreached edges. To solve this problem, we want the neural network to have a compact embedding layer, so it can handle high dimensional and sparse data. We may also want the neural network to include multiple metrics such that we can sample training data from different metrics, and they also provide a finer grained coverage than the single one. Then we have multitask neural network. This graph shows the architecture of our multitask neural network model. It has a compact embedding layer encoding high dimensional and sparse input. At the upper layer, it has three related coverage metrics which complement each other to provide a finer grained coverage information than a single edge coverage. For example, context coverage encodes the state of calling stack. Approach coverage encodes the distance of unreached branches. Let's look at the overview of our approach. There are three stages in MTFuzz. First, we train a multitask neural network to learn a shared compact embedding layer for three coverage tasks. Then, we compute gradient of compact embedding layer with respect to input to identify hot bytes and focus mutating on these hot bytes. In the end, we choose inputs which found new edges and add them into our training corpus to perform incremental learning. Next, I will explain the detail of three tasks in our model and how they complement each other and provide a finer grained edge coverage than a single one. Edge coverage is a common coverage matrix used in Fuzzer. It records edge transitions between each basic block. The graph shows a control flow graph of a program. Say we have the input, which execute through basic block 1, basic block 3, and basic block 5. Then its edge coverage is edge 2 and edge 4, marked in blue. Fuzzer maintains an edge bitmap to keep track of the edge coverage. In an edge bitmap, when an edge is exercised, it will be marked 1, else it will be marked as 0, and we can have bitmap like this. Now let's look at a case when edge coverage failed to capture the distance information of unreached edges. We first define an edge is not taken when its parent node is reached, but itself is not exercised. For example, edge 1 is not taken edge since the execution reaches its parent node, basic block 1, and pass along another edge 2. We then define missed edges as whose parent node is not reached and itself is not reached either. Edge 3 is an example of missed edges. Intuitively, not taken edges are more likely to be explored than missed edges since they're closer to the current execution path. But in edge coverage matrix, both type of edges are considered the same. To distinguish them, we propose a novel coverage to measure the distance of unseen edges to seen edges. For example, the not taken edges are one branch of current execution path, while the missed edges are two branches off. If one edge has a shorter distance from current execution path, it is more likely to be discovered. So we define not taken edge as 0.5 and missed edge as 0.25 to capture the distance information at this. Given the new approach coverage, we can preserve distance information and provide finer grained coverage. Next, let's revisit edge coverage. We show a case when it failed to detect the same edge from different calling stack. On the left is a simple code example. Say we have input 1, 0. We first execute through line 12, like this. Then line 2, line 3. Then we record the edge coverage L2, L3 in the table. Then we execute at line 14. Then we have edge coverage L5, L6 in the table. Finish the execution. Similarly, we execute another input, 0, 8. Start at line 12. We get edge coverage L5, L6 in the table. Then we execute on line 14. We have edge coverage L2, L3 in the table. Then we can find the two inputs actually have the same edge coverage, but they have different program behavior. Now, if you take a closer look at line 14, one input is 0, 8, like this. Note that the input is 0, 8 and the second byte is 8. So we go to line 2. And right now A is 8. So we go to line 3. Note that the address is an 8-byte long buffer. And we actually try to write 12 bytes to it. So a buffer flow happens. Now we know actually the two inputs 1, 0, 0, 8 have totally different program behavior, but they have the same edge coverage. Now the problem is How do we distinguish them? The answer is to define a new coverage. We define a context-sensitive edge coverage matrix by recording the calling context along with edge coverage, as shown in the table. Compared with vanilla edge coverage, context coverage records additional calling context ID as marked in red. It can complement edge coverage to preserve context information. After explaining the three individual tasks in our model, I will briefly introduce how we train the multitask neural network. A known issue for machine learning-based fuzzing is imbalanced dataset because the training samples are generated by Fuzzer, and the Fuzzer tend to maintain a minimum set of unique inputs. Here is an example. Say we have two edges, edge 1 and edge 2, and we have 6 inputs, input 1, input 2, till input 6. If you look at the bitmap, you can find for edge 1, 5 out of 6 inputs have label 1, and only 1 input have label 0. Similar thing happened for edge 2. Given such imbalanced data, the neural net model tends to lazily memorize the majority label rather than bothering to learn the difference of the two labels. So as a result, the model will constantly output the majority label. To mitigate this issue, we assign an adaptive weight to penalize the majority class when computing the loss. The weight is computed by the ratio of number of negative label against positive label. Now we can train our multitask neural network. The multitask neural network is trained by jointly optimizing all 3 tasks. The total loss is computed by linear combination of each individual loss. We assign equal weight to each task. Alpha here is 1/3. After the first stage of model training, we can use the trained neural network to guide mutation. The guided mutation is to focus on mutating hot bytes which affect program branching behavior. To identify these hot bytes, we compute the gradient of embedding layer with respect to input as salience score for each byte. The bytes with higher salience score will be mutated more frequently. The last stage of MTFuzz is seed selection and incremental learning. After identify the hot bytes, we choose the input which triggering the rear edges to mutate. The rear edges are those edges with least hit rate. Then we add inputs with new edge coverage and add them into our training corpus to perform incremental learning. This is our evaluation plan. We measure the edge coverage on 10 real-world programs. We measure bugs detected on real-world program 11M dataset. We also evaluate the contribution of each task in MTFuzz. Then in the end, we measure the transferability of multitask neural net model to a different program. We compare MTFuzz on 10 real-world programs against 5 state-of-the-art fuzzers for 24 hours run. The result shows MTFuzz achieve on average 2 times more edge coverage against 5 state-of-the-art fuzzer on 10 real-world programs. In terms of bug finding, MTFuzz finds 71 bugs, 11 unseen on 7 real-world programs, and most bugs on 11M dataset. In this experiment of the contribution for each individual task, we evaluate the contribution of each task by performing an ablation study on different task groups. The result shows MTFuzz with all three tasks can achieve on average 20% more 20% more edges coverage than a single task model. In the transferability experiment, we evaluate the transferability of neural model learned by MTFuzz. Specifically, we use the neural network model learned from source program and guide it to fuzz on another target program. So we compare it against one machine learning based fuzzer nodes and another coverage guided fuzzer AFL. The results show MTFuzz can achieve on average 2 times more edge coverage than other fuzzers. Takeaway: multiple coverage complement each other to provide fine-grained coverage. Multitask neural network can sample more training data than single-task neural network in fuzzing. Gradient of shared embedding layer is more effective than gradient of final layer.